Hi, my name is Anshul Raghav, and I'm a student at Redmond High School in Redmond, Washington. My project focuses on creating an AI model to help head and neck cancer patients receive more personalized treatment. In cancer, a patient's zip code can influence their outcome almost as much as the cancer itself. Head and neck cancer kills more than 400,000 people each year, and while immunotherapy can be life-saving, only about 15 to 20% of patients respond. Because these tumors are so close to the eyes, radiation therapy or spread of the tumors can damage the eyes, causing long-term complications. This makes choosing the correct solution immediately critical. Historically, treatment decisions have been made with either broad sequencing techniques or single marker tests. However, broad sequencing techniques are costly and slow, and single marker tests often miss key biology. This means many patients often miss effective therapies or lose critical time on therapies that won't work. To address this gap, my scientific question focused on predicting immunotherapy response without reliance on complex genomic techniques. While broad sequencing techniques capture all the necessary information, not all of it's actually required, which drives up costs by hundreds of dollars and delays results by weeks. QPCR offers a much better alternative. It can scan a small panel of genes quickly and at low cost, and is already part of many community clinics' workflows. Because QPCR can only measure a small number of genes, the goal of my experiment was to identify which genes were the most informative for predicting immunotherapy response. To do this, I combined 16 open source bulk RNA sequencing datasets, totaling over 1,000 patients and all their genetic information. When I visualized the dataset using UMAP and applied k-means clustering, some regions tended to favor immunotherapy responders, and some regions favored immunotherapy non-responders. I then used differential gene expression analysis to identify the 31 most important genes that separated responders to non-responders. I then used those genes to train an AI model that predicted whether immunotherapy would work or not, given RNA sequencing data. Then, I created a pipeline that allowed the model to work on qPCR data as well. The model matched or surpassed other recent models on metrics while remaining cheaper and much quicker. This is innovative because it contains the same level of predictive power as other recent methods, but in a form that is far cheaper, far faster, and actually usable in lower resource settings. For the hundreds of thousands of head and neck cancer patients, this tool helps doctors make the right decision sooner. Thank you for listening.